Delbert Larson, welcome back to the show.
Great to see you again, Brent.
Yeah, it's been a wild time in the world of physics, man. Something that you and I have discussed a little bit offline. I wanted to get your take on publicly is what do you make of that whole exchange between Eric Weinstein and Sean Carroll on Piers Morgan's show?
Well, it was quite interesting to watch, that's for sure. I haven't taken a deep dive into Eric Weinstein's paper. I did watch part of the iceberg that was put on uh, by the TOE Kurt on his uh, uh, online presence on Twitter, but I didn't dive much further than that. However, the arguments that Eric makes are certainly applicable to what I've faced in the review community, where you can't even really get past the editors to get a review in the journals that are high impact. They call them high impact journals. It's a real struggle even to get a review, and he's not wrong about that, because you should get proper reviews if their papers are going to be rejected. And that's and then it got kind of personal too, which is
Mm.
unfortunate, because science should be about objectivity, but unfortunately some subjectivity certainly comes in from time to time, so that was clear there.
Well, that's the downside of dealing with human beings as opposed to stuff like math, which is just it is what it is, right? So I think the human component is it's fascinating to me, and I think this is something that I would love to see you talk about more because your work is so rigorous and detailed, and it's difficult. It's not accessible sometimes for a layperson. Like I found myself struggling. I figure myself, I'm not the smartest person in the world, I'm not the dumbest, but I struggle sometimes to sort of comprehend this, or discussions on Kurt's channel, or watching Eric Weinstein talk, or any of the string theorists, right? Like it feels like there is a separate skill involved in discussing the material in a way that's accessible, right? And so that's one of the reasons I wanted to talk about it. Also, another reason I wanted to talk about this is because, as you mentioned, there's applicability here. There seems to be, I think Eric Weinstein has correctly called out, there is some sort of I don't know what's a word. There's like this intelligentsia that is like directing not only what you mentioned, like which papers get reviewed, but also where the funding goes. Like, what are we as a scientific community in the physics world going to study, right? And I think Eric's complaint is, you know, we have as a whole in the physics community latched onto the string theory idea, and excluded even considering alternative points of view, or theories or papers like Eric's and a bunch of other. I think there's what they take, like what loop quantum gravity is something that they're somewhat taking seriously, but beyond just a couple of things, it's like it's all string theory and nothing else. Do you see it that way as well?
Yes, well, there was a quote, and I think it was Newton, about "I've seen further because I stand on the shoulders of giants." And
Hmm.
people have taken that to heart, that in each subsequent generation, you're going to build upon the base of what those people did before you. And where we are presently is we've built somewhat of a Tower of Babel by just continuing to build higher and higher on foundations that we really should take some time to analyze whether we even started out along the right path. And that's where I see things today. And the other problem that you run into presently is it takes a very, very long time to learn the details of the standard model well enough to try to extend it. So you run into a second issue, because what that then means is you end up having to get a full PhD in the field and probably 2 to 3 postdoc periods before you can really understand it well enough to push it further along. And once you've got that much invested in the same structure of science, it's going to become exceedingly difficult to throw it aside and start something new. And it does have well, string theory, not so much, but certainly the standard model does have a lot to say, a lot going for it, in the sense that it does describe pretty much all equations except for, all experimental data except for gravity. And so you can hang your hat on that. On the other hand, you should take some time and take a pause at this, because it's got over 150 terms. It's got 19 free parameters. And at some point, if what you've done is you've started to build along the wrong path and you just keep adding terms and parameters, you're going to be able to continue to fit the curves. So that's something that should be people should be wary of going forward. And so that plays into all of this too. But then when you go off into string theory, because Eric still has a Lagrangian, Eric still does math, and he has an alternative mathematical model. And so I would kind of say he's somewhat of a cousin to the approach that they're taking now. When you get into what I'm trying to do, it's another species entirely, because I'm trying to model things with an underlying assumption that we start with a physical model, not a mathematical model. And that is totally alien. And the other thing about it is that frequently people start out that way. Even when you're in your 20s or something, you're normally going to think of the world around you as consisting of physical entities. What makes up the world? When most people are introduced to the idea of an atom, they think of the nucleus as a small ball containing smaller balls of protons and neutrons, and you might have little small balls of electrons rotating around them. You don't jump to the Dirac equation with 16 component matrices and 4 component spinors to say that that's what the electron is. You're thinking more in physical terms. And so what happens is, if you present a physical model to the present reviewers, they're going to say, well, this is clearly the result of someone who hasn't been trained, because it's so out of step with where they are today. Eric is out of step too, but it's more of a difference. It's a much slighter difference than making the big leap to going back to a physical model. So that's my little 2 cents on this whole debate.
Yeah. That's exactly what I was thinking about when I was watching that sort of debate. Right? Is that Eric is? It was hilarious because Sean Carroll is like, well, I've reviewed Eric's paper and there's no Lagrangian. He like listed all the things that weren't there, and I loved Eric's response. He posted all the references to his paper where it was clearly there. So Sean didn't even read his paper, or if he did, he skimmed it clumsily, right? Or the worst case scenario is that he was just straight up lying about it, which is hopefully not the case. I like to assume best intentions of people, but the thing that was driven home to me is, like you said, like they are still operating in the same sphere. Right. And it struck me as like a power dynamic. Like Eric is pissed, not necessarily because he claims to be 100% correct. And in his geometric unity thing is the ticket. Right. But he's pissed that he's being frozen out, where he feels like he is at least loosely affiliated with the physics community. I get that he's a mathematician. He's not, and I know there's some gatekeeping involved with that, but I think he's sort of pissed about that. And it struck me as a power dynamic where they're somewhat close together. Whereas I look at something like the quantum luminiferous ether model that you proposed, and that's, like you said, it's a completely different universe, right? And so I'm thinking to myself, if I'm sitting in your shoes, what hope is there of getting anybody to take it seriously and actually have it reviewed, and if it gets reviewed, having it being reviewed honestly and openly?
Well, thank goodness for physics essays, because physics essays does review papers that are outside of the mainstream, and the paper was reviewed there, and it got good reviews, and it found its way into print. The downside to that issue is it's not a high impact journal; it's a specialty journal, but it does have some very good works in it. It also has some works that are pretty far out there, and so then you get into that basket. But you kind of need to be, because if the present thinking is the one that's really far off, then anything that is correct is going to be look to be a big outlier and off on the wrong the wrong shoot of knowledge. So that's kind of where that is at. I haven't ever, I shouldn't say ever. Originally, when I would try to get things published that I thought were important, I definitely had a very negative feeling. I had feelings of some anger to it, but this has been now going on for so long that I just came to the conclusion the anger doesn't really help you. you might as well just put out there what you can. And I do really appreciate you having me on here today. It helps enormously to have somebody else look at your work to weed out the fact that maybe some of this is making some sense. I was on another podcast last week as well, and these efforts help because then we can start to get more and more people to take a serious look at it. That's what it's going to take. The unfortunate thing is the effort is rather large. When you the quantum luminiferous ether paper itself is 272 pages. Now it's double spaced, so but still, it's 272 pages. Now the upside to that is I put in all the intermediate mathematical steps, so you don't have to trust me. You can go in and you can, if you can do algebra, you can work out the vast majority of the paper there. But it also ties into some quantum mechanics I've done and this prion model that I have. So it gets kind of broad. So it takes a fair amount of time. And I'm now on my Twitter account, I'm getting people that are posting things to me to have me look them over. And sometimes they're very, very long. And I don't really want to take the time because you think it must be wrong. And so that's a big hurdle. And it's also a big hurdle. So it's a big hurdle that it's going to take a long time. And then you think it's going to be wrong. And the other big problem is there's just so many of these out there. I would not be at all surprised if there's certainly 100,000 because there's like 250,000 physicists and amateurs put out a lot of these sorts of theories. But normally I have found that if you take even 20 minutes on them, you can quickly find several pretty serious errors and you can eliminate them that way. So it's somewhat just being lazy. Now, the flip side of that is too, though, you point out the errors to these authors and they'll be back to you within a day and a half. They'll say everything's corrected or that they were right all along. So, and sometimes it's almost as obvious as 2 + 2 = 5 because, okay, I've redefined what 5 means. Well, okay. But you run into that sort of thing. So it's a real struggle. It's a real struggle, but it always has been. I mean, the Ptolemaic system lasted for 1,000 years. It takes a long time often to get things through. The bigger problem right now is the internet is such a sewer. There's so much information out there that to try to get your head above the noise, it's a struggle, no doubt about it. So thanks again for having me on.
Yeah, no worries. I'm happy to have you on, and I'm fascinated by the theory. I love, you've probably seen me post. I'm not a go with the mainstream type of person. I enjoy being against the grain a little bit and a nonconformist. I just have that streak in me, man. And so when I see something like this that actually looks rigorous and well thought through, and it actually flies in the face of conventional wisdom, I'm like, hey, let's take a look at it. I'm not necessarily accepting it, but I love exploring the ideas. But you did raise an important point, which I think is the mental model of a lot of people. When I had Lawrence Krauss on, I was talking to him about your theory, and he says nonsense. And then he talked about statistically speaking, most theories are wrong. And so I think there's a lot of people that number one, there's a vested interest in their particular theory and the thing that they're holding on to. So there's that component. It might be a financial thing, it might be a prestige thing, it might be their entire career is staked to this particular way of thinking. Additionally, though, I think it's easy to say, statistically speaking, I'm probably right if I say nonsense. So I think that there's a little bit of that at play as well.
Yeah, those are three of the big reasons, and then there's a fourth one you didn't necessarily mention, and that's that they really believe what they're doing. That's the more dangerous of all of the reasons, because if you fully believe that what you've learned is the greatest thing that mankind has ever produced, starting with Einstein, rolling through into Dirac, throwing Schrodinger in there, and then all of the additional advances that went into the standard model, and you follow all of it because the math is incredibly difficult. And then you realize that, yes, this all lines up with all these experimental data points. You come to this final conclusion that this is really true. And that's where you really face the opposition. If the people don't, if the opinion is that the one that's sitting in the physics chair that's doing the review doesn't think that they themselves are quite at the level of Dirac and Einstein and Schrodinger, but they're sure that they understand it all, and then they see something that's attacking these three giants that they revere, yeah, you don't have much chance. So you really need to try to have an open mind and say, well, there's something really wrong here. There's several things that don't work. We've got infinities that are being swept under the rug through a system called renormalization that the authors to that technique said was bogus at the time. And we've got these singularities in gravity and in the general theory of relativity that are going to infinity there. And then we've got a cosmological constant that's off by 120 orders of magnitude. And no one has ever been able, despite all of the interpretations, to make quantum mechanics make sense. And so with all of that, you should pause, have a little humility and say, well, something's got to be wrong somewhere. Maybe we should evaluate the fundamentals and try to build up from the ground up again.
Yeah, don't people in the physics community generally accept that as true, though? That for relativity does a great job explaining or making predictions about very 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 large objects. Quantum mechanics explains the very very small, and they realize that there are infinities and singularities in this math, which is typically in your field an indication that you made a mistake somewhere. Right, like there's something's wrong that needs to be resolved. My understanding is that that sort of uh, endeavor to sort of reconcile quantum mechanics and relativity is where string theory emerged, and why string theory became um, in vogue is because it came up with a number, right? Like when you do the calculation, like you can resolve it at least mathematically, at least theoretically, and what appears to give it as much runway as it has without any sort of experimental validation is the fact that it's very difficult to validate experimentally due to the energies required and various things. And so that's just my lay view of it. Do you see it any differently? But it seems like to me, like that's the reason why string theory has gone wild, is because it's very very mathematically rigorous. I think Eric Weinstein even says like the people that are doing string theory are really the smartest people out there. And the fact that you can do that, the dog ate my homework thing, and there's never, you don't have to come to the table with any experimental validation. You have I don't know how long before we could validate it, right?
No, you're right about that. And you're right about the fact that these problems are noted. The thing that I rebel against, though, is that when the solution involves expanding the number of dimensions around you to something that you cannot see and saying it's compactified down to the three that we do see and then time, I think you've just what you have done is you've now introduced, for each dimension you introduce, you're introducing another infinity. Because if, for instance, if you were a plane figure on the top of a flat table and that was your universe, if you now add the third dimension, it goes on to infinity, up and down, perpendicular to that table, to an infinite amount. So every time you add one of these dimensions, that's what you are doing. Now, is it possible that that is the way reality is? Well, maybe. But my take has always been that we should play within the rules of the world we live in. And we rather obviously live in a three-dimensional world where time is completely separate from space. Now, the fact that it's obvious does not mean it's right. But I still revert to the fact that it's obvious makes it more likely to be right than saying it's wrong. And that's kind of one of the places that I depart from. So if you're going to take the point of departure that I'm taking, then you really have to go back to the fundamentals, where what string theory and all of these other theories tend to try to do is they try to replicate this overly complicated Lagrangian. They try to replicate general relativity as some sort of collapse of some structure that they mathematically derive prior to it. And that's an entirely different approach from what I think physics should be about. But I am clearly in the minority on that one.
Right. And I think it has played out in the past that simplicity seems to reign supreme when it comes to explanatory power, right? Like when you start to see additional complexities added, that typically means that you're off somewhere. How do you view that?
I fully agree that I have a very strong belief that when you end up with, at the end of your theory, if you can simply describe things, you probably are on the road to truth. But for me, what I consider simple is to say, again, if we go back to that example of the hydrogen atom, that we've got a proton at the center and an electron going around it, physical objects. We have two physical objects that are interacting with each other. We might have a neutron in there if it's a deuterium isotope of hydrogen in the nucleus, and then maybe we've got three objects, but we're starting down the path of having a very small number of the physical building blocks that make up our world. When I saw Kurt and Eric discuss his theory, and they were mentioning how simple it was, I was kind of taken aback a little bit. In fact, I commented on their post by pointing out that they must mean that their starting simplicity is a series of postulates or principles that they're building on, because the end result that has something that may have 200 dimensions in it and multidimensional time, to me, that's a very complicated world, because that's, especially if you're saying that those things actually exist in reality. So for me, the simplicity involves physical entities, time, space, the particles that occupy it, perhaps waves on those particles. That's where I have always sought the simplicity. It's not been in the math, because to me, math is a tool to analyze the simplicity of the ultimate building blocks of our world. And then math takes those building blocks and then leads to the expressions that we can then do tests against. So that's my view of simplicity, which is, again, different than what's out there now, because what's out there now is everybody's searching for these simple principles, and that a lot of that goes back to Einstein, because he replaced two ad hoc proposals that were perfectly good at explaining the Michelson-Morley experiment by two principles, and that was just a foundation, and people loved that because it said that our reality is somewhat grounded in these principles that we go forth from. But I do reject that starting point. I think nature itself, again, to reiterate the point, is made up of elemental physical entities, and that's where we should look for our simplicity.
Yeah, for sure. And one of the simple things that seems to be a point of divergence between the way you're looking at things and the way standard model looks at things is around light and the way it propagates. Can you explain that to me? Like what the difference is as far as a vacuum versus transmitting through a medium?
Well, okay, so if you transmit on a medium, things should be fairly clear almost intuitively. If you were to take a guitar string and you pluck the guitar string, you're going to have essentially one wave moving in one direction and another wave moving in another direction. And then when they add up, you're going to get the vibration that you see. And what you have there is you have the displacement of this solid string, and that's what's causing the wave. When you have a water wave, you've got displacements of the water molecules that you watch. When you have waves in sound, you've got other waves that are compressional in nature. But all of these things involve a medium that's doing the waving. So that's the approach I take with an ether model, and it's the old approach that people thought led to the idea of the ether. Was we're seeing these waves, they interfere. We can tell their wavelengths and frequencies, and therefore the thought was, well, something must be doing the waving. So that's that approach. The Einsteinian approach involved really just a system that ended up deriving the equations for what is going on. And so his view was that from the starting two principles, the first one was that the light is constant in all frames of reference. The second one was an invariance of the laws of nature's laws. One of nature's laws, or set of nature's laws, are encapsulated in the Maxwell equations. And the Maxwell equations, if you derive them in the right way and you don't have any sources, will lead you to an equation for light. And so what you end up with then is you have, again, you start from this principle, these principles, and then you derive the math, and then you say that in each frame, Maxwell's equations are invariant from one frame to another, and they are what describe light. So you get away from the idea of a physical entity. Now, what you also have, though, in quantum field theory is you have these fields. They're essentially mathematical descriptions of something. You don't necessarily want to say what they're a description of. And then you can excite those fields with a certain amount of energy. And then you get an instantiation of a quantum of that field. And then a quantum of this electromagnetic field is then a photon of light. Whereas in the ether approach, you've got vibrating wave packets. So the vibration itself is over a finite spatial size, and you can analyze it that way. So I hope that gives the flavor of the difference between the two ways of looking at that issue.
Yeah, it totally does. And by the way, people may not be familiar with Maxwell's equations, but those are basically governing electromagnetism, right?
Absolutely, yes, yeah.
Cool. And so
Electricity
I just
matter.
wanted Yes, one of the when I'm reviewing this material, sometimes people, especially that are trained in physics, they say things, speed by it, and I have to go Google stuff and figure out what it is. So I want to make sure the audience is just tracking. So why did people abandon this idea? Because your theory is sort of a reboot of an older theory about luminiferous ether, right? And so why did we abandon this? Because it's intuitive, right? Like we understand generally, like, things have to propagate through a medium if it's going to be a wave. Does it have to do with like the double slit experiment where there's like a dual nature with respect to quantized light photon packets, right? Or whatever. I don't even know how to describe this. I don't have the right terminology. You understand that there's a way that it can be a particle and a way that it can be a wave, depending on the situation, the whole observer effect thing. And so I'm trying to figure out, like, what was the big fork in the road that caused people to abandon that? Was it literally just Einstein's relativity?
Yes. So you kind of jumped ahead on the story because the
Whoops.
first, yeah, well, no, it's great because you kind of jumped ahead to where the problem lies. But in fact, had that problem been really appreciated first, I'm not as certain that we would have gone down the relativistic path. The history of it was that it's very famous. The Michelson-Morley experiment predicted a result that we would see as the Earth goes through this solid. And then Lorentz, Larmor, and Fitzgerald all came up with proposals that as bodies go through the ether, they shrink in their direction of motion. And as clocks go through the ether, they slow. But those were ad hoc proposals that explained things, but it didn't have a good, it's like the 19 parameters of today. But there were two there that you say, well, where are they coming from? And then Einstein, it was a very beautiful thing that he did with his two proposals, because he ended up arriving at the same transformation equations that Lorentz came up with in his special relativity. It was known prior to Einstein's derivation that the speed of light would be constant in any frame. And Einstein essentially then took that as a postulate, ran the derivation backwards to get to the Lorentz equations. So that was step one. And the other thing, there was something about that I needed to mention. Oh, the important thing was that if clocks are running slow and the meter sticks are shrinking, Lorentz viewed this, that the only measurements you could really trust would be where those entities did not shrink and the time did not run slow, and that would be at rest with respect to the ether. But you couldn't tell if you moved with respect to it, because the way the equations work out, it was impossible to tell. Whereas in Einstein's case, instead of saying that one of them was correct and all of the rest of them were wrong, but you couldn't tell, Einstein said, well, they're all equally valid. And what that then meant was that time and space themselves change into each other, which is a rather difficult concept to wrap your mind around. So to get back to your question, so what happened at that point was it wasn't adopted. It wasn't adopted at all to speak of. The theory was out there. A lot of people thought it was very beautiful. It tied into some ideas that Kant had about space and time and some of the philosophy that was going around prior to it. And it was very interesting. But what really tipped the scales to get rid of the ether was, it's also famous, was Eddington's experiment with the eclipse, where Einstein had predicted the bending of light, and it came out to be correct by his theory. And that's what really threw it in Einstein's favor. But in my view, the more important thing that Einstein had done was he solved the problem of the advance of the perihelion of Mercury. So again, for your viewers, Mercury is a planet close to the sun, and it has an elliptical orbit. And if you add up all of the tugs and pulls from the planets and the sun and everything, that elliptical orbit should have its furthest point drift a little bit over time. But all the calculations were very carefully done, and there was an anomaly to that, and it couldn't be explained. And Einstein's relativity did explain that. So you now had, in general relativity, you had that backing it, which made people take it considerably more seriously than they did just on the simplicity arguments of Michelson-Morley. But then when you had the light bending work out as well, that was another data point that was very significant to the acceptance of general relativity. And then as late as in the 60s, there was an experiment done bouncing light back and forth from the Earth and Mercury and grazing the sun. And it was done by a man named Shapiro. And that Shapiro effect showed that the light bouncing back and forth took a little longer if it got closer to the sun. It slowed down by the sun. And that was also a prediction of general relativity. So you had three major experimental tests done that supported it. And then the fourth thing that really supports general relativity is they call it a relativistic time dilation. If you have a photon leaving a massive object like the sun, by the time it would get to the Earth, it's going to have somewhat of a redshift, and that was predicted by general relativity. Now, that one's very easily described by giving the photon a mass and then having it be gravitationally attracted to the sun, and the work done then on the massive object by the gravitational field will lead you to the same exact result. But that's the body that all went into the abandonment of the ether, because special relativity did it by simplicity, and then Einstein's general relativity had real good agreement with all the experiments that people were wrestling with, finding answers to what was going on.
Got it. And so the question I would have is, how would a luminiferous ether theory explain the same phenomenon?
Okay. So one at a time. I just did describe how it handles the redshift of light. It's a gravitational attraction from the photon to the massive object. And then if your clocks are based, as atomic clocks are, on light, then you're going to end up with the gravitational time dilation, and you're not going to have to think you've got a problem with your GPS units because of it. So that it handles that in that fashion. And then for the advance of the perihelia, I didn't really know, I didn't put this in by hand, but when you derive, okay, so in the quantum luminiferous ether, what happens is that gravity will weaken like a quantum field and a tension field. At the very heart of the ether, there's a tension field that's trying to pull the quantum in on itself. and there's a quantum pressure that's trying to push the quantum of ether outward. And in equilibrium, those two are going to give you a size. And what happens is if you've got mass in that quantum of ether, it's going to affect both the tension and the quantum by reducing both forces. And there's some support for this because if you heat up a spring, you get less of a spring constant. And also, if you have more mass in the quantum field, you reduce the quantum pressure. So that was a proposal for the very basics of how mass affects the ether. And then through the derivations, I found that proposal. Oh, and then the important thing too is that there's two types of ether, and one of them, the quantum force is slightly greater than the tension, but the change in the quantum force is slightly greater than the change in the tension force. And in the other type of ether, it's reversed. And when you run all of the math, you end up with Newton's laws of first approximation. But the other thing that you end up doing is the ether itself is going to move because this effect leads to the positive ether expanding and the negative ether contracting around massive bodies. So those ethereal quanta are going to move with respect to their original position. And as they move in the presence of fields, there's going to be work done. So the work is going to give you an energy change, and that energy is going to be stored within those quanta. So now you've got an energy field at every quanta when they've been moved by gravitational forces. And you end up then with this energy field, well, by E equals mc squared, that's a mass. And so you can get a field mass that exists around the bodies. It's very weak, but there are two components of it. One of them's negative and one of them's positive. And one of them falls off as 1 over r. Newton's law falls off as 1 over r squared. And then there's a third term that's negative that falls off as 1 over r cubed. That latter term turned out to be exactly what was needed to get the perihelion right. So that was kind of a long description, but that's how that came out. But as you can see, it was a very natural result. And of note, the 1 over r force is exactly what you need to determine dark matter. So you get both of those results you get all three. You get Newton's law, you get the perihelia advance, and you get dark matter from a very simple physical underlying cause. And then as far as Shapiro goes, the speed of light in the ether model is going to be the square root of the tension divided by the mass. It's the tension per unit area and the mass per unit volume. You take the square root, normally you get the speed of light to be what we now know it to be. But when you get closer to gravitating bodies, the mass will increase, and that's how you get the slowdown of the speed of light as it goes by the massive object. So that test is also easy to describe in a fairly straightforward way. And then the last test that we have is the speed of is light bending around the stars. And for that one, I had to add an ad hoc proposal that was very specific on what happens when bodies move through the ether in the gravitational realm. There is going to be a flow force as bodies flow through the ether. There should be some sort of force, and I use that fact that it existed to fit a model for the effect that gives us the right result. That is one of the things that could certainly use more study. There's a flow law for electromagnetism that works very well and makes a lot of sense. And it's a very physical law. So that one's very clear. But the one to solve the light bending, I will readily admit it's an ad hoc addition. But theories often have those. And it's still quite a simple theory to get to all of the equations. Because unlike Einstein, who accepted that the laws of nature should remain the same in all frames, the quantum luminiferous ether derives them. And it derives them from these physical arguments and a very small number of initial postulates. So the fact that there's one additional one for light bending, it's unfortunate, but it's still a small set to get to where we need to be.
Got it. And that makes sense. And maybe now is a good time because as you were explaining that, I was thinking to myself, like I sort of followed you because I've looked at your work and and I've seen the representation. So maybe we should take a moment and talk about the Aetherions, right? I understand that you called them out. We called one of them positive, one of them negative, and maybe you could just talk about the lattice structure and the nature of Aetherions.
All right. So this the description that we just had about the positive ether and the negative ether, and one of them shrinking and the other one expanding under gravity, goes back to the very start of what we talked about even before we did that, which is that an individual ethereal quantum will have a tension pulling itself in and a quantum pressure pushing it out, and you're going to get some equilibrium that's going to give you, I like to analyze it in terms of cubes, and so you get an equilibrium cube size. And then those cubes are all going to exist within an enormous solid. It's the solid that's around us all of the time. And so it's a quantum solid, not that different than, say, your table, or a solid block of wood. And that's what the ether is. It's an enormous solid at very high density. And that's the basis of it. But it is possible, if enough energy is put into the ether, to knock out one of the positive ethereal quanta and one of the negative ethereal quanta. And I dubbed those to be called Aetherions not that long ago. It's another paper. And it turned out that those two Aetherions could either be existing by themselves in outside of the ether. And actually, I shouldn't really say outside. I mean, they're still embedded in it. They're just not attached to it anymore. It's somewhat like electrons flowing through a wire. The electron is still inside the wire, but it's no longer attached to the ions. So you can think of the freed Aetherions in that way. It's like you've got a free chunk of ether, one unit, one quantum, flowing through the rest of the ether. And they can exist by themselves, or a positive one can orbit a negative one, or a positive can orbit a positive and a negative could orbit a negative. And if you included the orbital angular momentum of those orbiting bodies and their spin, it turned out that those configurations of these two Aetherions made up what I had called preons in another work. And what the preons were particles that were those that made up the quarks and leptons of the standard model. So the picture then is that everything you know of in the normal world is made up of molecules and maybe an occasional atom, and then the noble gases. But then the molecules are made up of atoms. The atoms are made up of protons, neutrons, electrons, and then the present science says that the nucleus is made up of quarks and the electrons are leptons. And then if you smash them together, you can get cousins of the electrons and cousins of the quarks. Well, the preon model said that the leptons themselves were made up of two preons in different excited states, and that's how they got different masses. Otherwise, they would be identical. And the preon model used the same preons plus a third preon to make up essentially the quarks. There's a bit of a difference there because the quark never really exists. What really exists is there's a central preon, and it has other preons orbiting around it, and the quark is a portion of things that are made together. But in any event, everything then is now at this point made up of these preons. And then I found that the preons themselves were made up of these two Aetherions in different configurations. And so the picture that you're left with for the physical picture of our world is that we're living in a giant solid ball that is always made up of these two Aetherions, one positive and one negative, close next to each other. Occasionally they'll bounce out, they'll form these things, and that's what we see as matter around us. So everything is made up of these two things. So it's, from a physical standpoint, it's exceedingly simple. And when that came out, I rushed to get a paper out, and it's not published yet, but it's been approved, because I think that's about as simple as you're going to get. And then beyond what makes up the particles, what you also have is you do have waves upon the ether, and that's what light is. That's what gravity waves are. And I'm banking on the fact that that's probably what neutrinos are as well. So then that's everything. So you have waves and you've got these Aetherions, and then you do have the fields that are inside the ether, but that's it. You don't have, in no new dimensions, you don't have to change your thoughts on space and time. And it's just a very simple physical picture. And that's where things are right now.
Got it. But simple to you, but you broke my brain a little bit. And this is what I've been struggling with. I'm looking at your model, right? I'm looking at the lattice work of the ethereal quanta in a cube, right? And I'm trying to conceptualize. Like you're saying, like, look, this is all a giant solid. And when I think of a classical solid, like a platonic solid, like it doesn't make sense to me. I feel like there's a disconnect in my brain because your diagrams on your website, right, show these cubes, and it totally makes sense to me. I know what a cube looks like, and I'm assuming there's other cubes all around it connected in some way. I was assuming that they would move against each other, like you like way you can stick your hand through sand, where sand is like these little tiny cubes, but you can move through it. So can you help me with that? Because like that part is still unclear to me. Like I tried my best to understand it, but it's still when you start talking about our universe being a giant solid ball, like that's not making sense to me.
Are you familiar with ionic solids like salt?
Yes.
Okay, so it's not that different than that at that level on the original lattice. And then the second thing that would happen, you can understand how you could get waves on that. You start getting displacements of the ions, but they wouldn't go
Mm-hmm.
very far. And in the ether, it's going to be the same thing on that score. The problem that you're wrestling with is if you now have a freed ion, in this case, a sodium ion, say, and it would then enter that lattice. This is where it gets a little different because the sodium ion would now occupy the same space, but it would go through the same physical space as the sodium ions that were in the solid, surrounded by the chloride ions. And what it would do is it would then cause the original sodium ion to expand in size. So it could fit in the same space because they have a repulsion, and it would bring in some of the chloride ions to counteract things to make sure that the charge is always neutral. And the other complicating fact is that the free one is probably it's not going to have the same size. It's going to be a lot larger. So you're only going to have a small portion of it overlapping all of the ones that are still in their solid state. Certainly seems probably difficult to follow from a sodium and chloride solid lattice. I use that example because it's something, and this just now occurred in my head, so I'm kind of winging it here. But that occurred to me because it's something you can get your mind around to start with. Because the complicating factor of this thing occupying the same space, that's what happens in atoms. Electrons will occupy the same space, but they've got different quantum states. So you can have the same particle because it's a wave, and it's got a density, and you can overlap them in the same space as long as they're not in the same state. For the electrons in an atom, if one's spinning one way and the other one's spinning in the opposite direction, they can be in the exact same physical space and they're fine. And this is just a quantum rule that we have found that exists in normal matter. So that same principle is what I've just described about the free Aetherion, how it can fit in the same space and then move through the fixed one. So that's the picture to have on that. And then on the cubes, the thing about the cubes is that it's a reasonable starting place to do the analysis from, and everything follows and everything works and all the derivations go. But when you really get down to asking the question, well, is it really a cube? That's a very complicated question because the answer is probably not. You get into a situation of perhaps there's several of them in a larger cube, and they also occupy a quantum state. But I don't get into those details because they're not that important, because you can leapfrog your analysis back down to an assumption where now that cube is not the actual physical cube, but it's a representative cube. And then you can take that representative cube and then tie it back rigorously to a larger one that has multiple quantum states within it. And I did that when I did the analysis of white dwarfs. And so if you want to get into the details, that's where you would see that. I have not referred to it in the Ether paper because the Ether paper keeps this whole modeling simple, but that's the long-winded answer to that question.
Got it. I think I'm tracking you. So I wanted to get more philosophical here, and I'm very curious how these ideas grip people. My experience in the world is that like you don't seek this out. It's almost like these things seek you out and use you to sort of advance them. And so I want to get your take on that. Like, how did you get gripped by this? Because you're definitely passionate about it, and uh, it you know, let's be fair. Like, it may not get universal adoption. It may not go anywhere. Where you know, I'm just being fair. This is a likelihood. And so you're putting so much energy and time into this, and so I just want to understand, like, from your perspective, like how you got gripped by this and why it's so important to you.
I've always had an absolute obsession with trying to understand the world around me. And if the stories that I'm being told have the problems that we alluded to earlier, I just didn't think that was the way it worked. And so, and when I saw the Lorenz's work originally, I can remember I was a sophomore in college and I asked him, well, why did his work go down instead of Einstein's? And they said Lorenz was discredited. And I'm going, well, discredited by who? You know, now we discussed why, but when I first learned it, you know, that was like, okay, that's one bad step. And then when I learned about the ether theory, I thought, well, that makes sense. And then I was going down these classes and they did not make sense. And there was no, and the bigger problem was that in graduate school and really even in a senior level and even maybe a junior level physics courses, things started to diverge from this physical model we've been discussing. And no one ever really said what it meant. And I couldn't understand what it meant. And when I saw the Dirac equation with those 4-component spinners, and none of the terms was supposed to necessarily line up with anything physical, and the matrices were only there to linearize a nonlinear equation, I started losing more. And then when you get into general relativity and there's a tangent space that, okay, that's what Riemann had on a curved surface to do some analysis, but then he threw in a cotangent space, and where did that come from? And why was that even be related? And what's not explained is it's just a mathematical model. And so it was a math class. And then at that point you realize, oh, so now the question goes back. Well, what is the world like? And it was just an obsession. And if there's something that's not making sense, I'll just keep beating on it until I think it does. Or, like I mentioned earlier, there are times like that, the one ding on it right now with the ad hoc law. At some point you say, well, you know, you put this out there and say, well, this is an ad hoc law, and somebody else can maybe make a contribution. But the driving thing always has been to just try to understand what's going on. And quantum mechanics is tied in with this, because if you have an absolute time, and we go back to that, it's very easy to understand quantum mechanics. It's very easy to understand what's going on. You've got a distributed wave function that collapses in a faster than light way. The whole reason you can't have that is relativity says there's nothing faster than the speed of light, and it's baked into relativity's cake. So one of the two had to go, and everybody's been trying to get quantum mechanics ever since it came out. But the one that needed to go, in my opinion, was relativity. So that's what it is. It's a drive to try to understand. You know, I mean, I think a lot of people have. You may have that in your life, right? There's things that you just want to understand.
I'm cursed with it, man. But I want to understand everything. That's my problem. I'm not specialized in one area. I just want to know everything, and it's terrible. It grips me sometimes. Uh, anyway, like I want to talk more practical, right? So, from a so what standpoint, I know you're interested in a different field of study, or not. It's related, but slightly more practical application. Maybe I've seen you talking a little bit of smack to Elon Musk about his obsession with solar, as far as the power generation of the future. Why is he wrong?
Well, I don't necessarily know that he's fully wrong. It's just I think fusion is a much better solution for mankind's energy needs if we can make it work and harness it, especially for his dreams, which are to go to another star system. Because as we get further and further from the one that's near our home, it's going to get dimmer and dimmer, that being the sun. So the source of the electricity as we go out is going to dim, and I don't see how that's going to be particularly useful. And I've seen solar sails, but that's going to dim too. Whereas if you had a fusion drive, the products coming out of the fusion reaction are already moving at significant portions of the speed of light. So you can use magnets to take the charged particles and steer them where you want to go, and you can get your starcraft to head where you want it to go. And there's interstellar hydrogen. You can pick up your fuel along the way. So if that's your goal, trying to get fusion is much better. Here on the planet, to get back to something more close to us, if you could take and drop a fusion system inside of an already existing coal-fired plant, because it is about the same size, then what you have accomplished by doing that is you can use all the existing infrastructure. You've got a plant in the middle of the city. You don't have to get a lot of solar panels up. I don't know myself what the lifetime of solar panels are going to be in the wild. There's the argument that you can put them on roofs, and I'm sure you can, and I see them. I also know, living in Texas, how long roofs last. And it's not forever, and you can run into problems. And so I don't know what the costs are going to be. I do know that solar would require a fairly large amount of area to cover our needs. Sometimes the sun doesn't shine. And so you've got those issues as well. I think there's some mining issues of certain elements that run into problems there as well. And so I've always thought that the better solution, if we can get there, is fusion, because the energy that comes out is very dense. And so you don't need a lot of land use. You can put it close to the cities. You've already got your wires up to take the power where you need it to go. So that was always something I wanted to try to work out.
Got it. Yeah. So what are the problems today or limitations around colliding beam fusion?
Well, colliding beam fusion is right up there with the ether as being something that was thought of long ago and investigated and then discarded for good reasons, and then it died. And in the colliding beam fusion case, the reason the idea was discarded was, if you've got two beams colliding with each other, then every once in a while, if they hit, you'll get the fusion event that you're looking for, and you'll get a lot of energy out, and that's what you want. But the vast majority of time, they're going to miss. And
Or
when they
ricochet,
miss,
right?
yes, exactly. But the ricochets are lost. But they're also small. So there's a small chance for them to hit, and there's a small chance for them to be close enough to not make it and ricochet. But what really gets you is something that misses by quite a bit. Because what happens when they miss by quite a bit is they're coming along straight, and all of a sudden they get a little kick. And it's not enough for them to leave the system when it happens once. But what happens is you then need to steer them around for another try. Because if you don't steer them around for another try, then you lose all the energy you put into them. So your system's not going to work. And when you steer them around for another try, they do it again. And then they do it again. Not only that, they do it more than one time as you're trying to make the two beams go against each other. And that's called multiple scattering. And it was shown that process is going to lead to more energy loss than you're ever going to be able to get out of the fusion system. Now, that's not totally true, because, of course, there's energy conservation. So you're always going to get some more energy out of the system, but you have to get enough energy out to overcome the Carnot limit. And so you need about twice as much energy out as you're going to get energy in. it's going to kill you. Those multiple scattering events just are not going to make it work. So the idea was set aside. And then my thesis experiment back in grad school was on a technique called electron cooling and we were going to do it for antiproton beams at Fermilab. And in electron cooling, what you do is you take an electron beam and you superimpose it on top of an ion beam. And then what happens is they're moving along at the same velocity and they're overlapped. And if the ion beam had one of these kicks that we got from the multiple scattering, and it's going to work its way against the electrons, it's going to scatter off the electrons and it's going to straighten out. And then what happens is that error is then error in energy is then transferred over to the electron beam. But the electron beam is a single pass system. You bring it back to a collector and you collect all of the energy of the electrons that you can. Now, there's some loss in that process, but you've now straightened out the ion. In fact, you've straightened out all the ions in the beam, and you can bring them around for another try continuously. And I worked out all of the math of that entire apparatus, all of the various processes, and I finally came up with a design that got a gain of about 2, which could make it possibly work. And there are definitely ways of improving it, but I thought at that point it's time to try to get some money. And I thought it was a no-brainer. This thing was supposed to cost in the neighborhood of 10 or 20 million dollars, when for the fusion events, the big tokamaks that are being worked on, the number is usually in the billions of dollars. But to my shock and surprise, I couldn't get a dime. People were always very interested, but the barrier, and I think if it would have been $100,000 or $500,000, I think people may have jumped at the chance. But it was too much money from the group of people that I was pitching it to make that attempt. And then the other thing that has happened is during my entire life, fusion. The joke always was that fusion was 20 years away and always will be. Lately, the hype monster. So now it's 5 years away and always will be, and you hear it all the time. And I've heard these now for I think it's at least 20 years that we're 5 years away now, and it's because it's a very, very difficult problem to try to control a very high density of ions and electrons called a plasma at a hot temperature with a magnetic bottle. And it's tantalizing because it seems like it's not that far away, but to actually make it work has proven very difficult. So I still advocate for trying colliding beam fusion again with this new idea of using the electron beams to take the energy away that were going to kill the idea in the first place. And it would have done it in practice. But if you can find a cure to that problem, then this offers a great solution. And the other thing about it, especially circling back to Elon, is these systems, the tokamaks are enormous to get the power out. This system, well, most of them, I think there's been some work on compact ones as well. But this system with the colliding beams is much smaller. It's modular. So you're looking at maybe a megawatt per unit. And then again, you can direct the products of your reaction to steer your ship, provide power for it. If you're looking at interstellar travel, it's something that people should take a serious look, even if the tokamak works, because it ends up with the particles coming out are much more uniform in energy. So that has advantages if you're trying to steer and propel a spaceship. So that's that use. And then of course, if it's working, you drop them into your coal plants and no more emissions, and you don't have problems with any nuclear accidents, because it's hard enough to get these things to work. This is not built on a chain reaction. There's not going to be an accident in that way on a fusion plant.
Right. And is there any waste emitted from a fusion reaction?
There is. The problem you have with the fusion is normally you're going to have a deuterium that interacts with a tritium ions, and you're going to produce a helium ion, and you're going to produce a neutron. The helium ion is totally benign. The neutron, however, can be a problem. It can activate other long-lived nuclear materials, but it's not like fission where you're producing them directly. And if you use the right materials to surround your fusion device, you can preferentially make it such that the neutrons won't activate anything to a long-lived state. So while there is that issue, it's much smaller than a fission plant, but it's not something that we shouldn't be aware of. We need to definitely address it. Now, one of the advantages ecofusion has, the colliding beam fusion has over the tokamaks, is that the colliding beam system is a free system where we're not trying to confine anything. We're trying to focus it to a point. And since we're doing that, we have greater freedom on the things that are close to the collision point itself. Whereas in a tokamak, you've got to make sure you're ensuring this very high magnetic field. So you've got to have the materials in place that are capable of producing that magnetic field. And then that means you've got only your choices of materials are going to be smaller than they will be for a colliding beam fusion system.
Got it. So how big does would one of these hypothetical colliding beam fusion systems have to be? I'm trying to picture myself in the SpaceX ship. What's the size? What's the form factor? How does that work?
My recollection, and I didn't look at it, I didn't study right before the interview, is that it was 1 meter high by 3 meters wide by about, I think it was, let's say 15 meters long. So it's long and narrow and not too high. And by using magnetized cooling and proper focusing elements, it conceivably could produce close to a megawatt of power. Now, and I have looked, because the thing that would be ideal is if you could get a 1G acceleration of your starship, because then you'd have gravity for, people need gravity. But I looked at that. That'd be a monster. So I don't know how many of these units you would need to get to great speeds, but that's the size of one unit right now. And the other thing, of course, is that the first semiconductor chip was it fit in your hand. It was about, So as once you establish the foothold of getting one of these systems to work, engineers and people are smart, and they can tweak it and push it. And the one thing about this whole approach that's different from the tokamak is that every ion can be accelerated to a situation where when they collide, they're at the peak of the cross section to produce fusion. Tokamak is a thermal device, so it's got a very random set of velocities, and it's based on that. Also, on this colliding beam system, when we're likely to find that we're getting some beam losses at certain spots in the ring. Well, now you put in some magnets and steer them back in, and every step of the way, you on your magnets that you use to recycle them, you can make them into permanent magnets. You can make them into superconducting magnets. Every step of the way, you can look at how to limit the amount of energy you're putting in, and you can continually push to get higher energy out. So the first step is to try to build the first system and see how close we can get, start taking the measurements, find out what we need to improve upon. And then even further along the path is what you allude to, which is, can we make it smaller? What else can we do to make the focal point tighter? Can we get more power out in a smaller system for propulsion? All of those things. And it would be a very exciting path for mankind to pursue. And that's the dream.
Yeah, the opportunities seem pretty endless if we can get that cracked. It seems like human beings' big bottleneck is energy right now. It's you have relatively cheap, abundant energy source, and you've solved a lot of humanity's problems. So that's super exciting. I want to get into a different area though. Are you familiar with Dr. Jack Kruse at all?
Nope. We'll have a new one now.
I want you. I definitely want to steer you his way because he's an interesting guy, right? So he is very much. Well, he's an anomaly. How do you describe Jack Kruse? He is a neurosurgeon by trade. right? Been doing neurosurgery forever. He is Rick Rubin's personal doctor. If you know who Rick Rubin is, he's like one of the most famous music producers in the world. And Jack Dorsey, the old CEO of Twitter, he's his personal doctor. That's the reason why he didn't get canceled during COVID. Jack is very much anti the COVID vaccine. He was on with Mary Bowden, who I don't know if you know, she was recently on Rogan, I think like 2 days ago, and she was one of those doctors that ended up getting in a lot of trouble during COVID for treating people with non-conventional therapies and was against vaccine mandates and things. So he's kind of in that space, and he's very influential, or he was, with the origins of the Maha movement. Robert F. Kennedy Jr. And some of those people in that space. He was on a very famous podcast with Danny Jones with Cali Means. And he's not a fan of Cali Means. He's a very caustic, abrasive old son of a bitch, but he's very smart, and he's very much in the world of physics with respect to biology. So he turned me on to a book, a guy named Robert O. Becker. Is a book called The Body Electric, and it talks about electromagnetism and light with respect to human biology, and he's looking at it from a completely different way. He's very into mitochondrial function and the physics of that. He talks about the effects of deuterium depleted water, and like he's completely down that rabbit hole, and he is skeptical of Elon's ambitions to go to Mars because of biological constraints around. We talked about this a little bit offline. The effects of gravity, number one, light, two, and then number three is magnetism. Right, so magnetic fields of the Earth, which we've evolved around, and the sun's effects, and those sorts of things. And he's very skeptical that we're going to make it on a planet like Mars. So I would just love to get your take on that. I wish you had been exposed to his work ahead of time, because I'm fascinated by the subject. This intersection of physics, and biology is super interesting to me.
Yeah, that's great. I after your last podcast, I followed up on all of the things that you mentioned to me, and I'll dig into that as well, and I'll see. I'll have to get back to you at a different time on that one, because it is all new to me. So it sounds very interesting. So it'd be good to become acquainted with that. Thank you.
For sure. Yeah, I'm probably going to lean on you if you have a chance to review some of his stuff. Trying to talk, to Jack on Twitter is very difficult. Like I said, a very ornery cuss. He's incredibly opinionated about certain things, and I'm not nearly as smart as him. And so trying to get my my brain around some of the ideas that he is forwarding. And it's not just him. It's like I said, he's sort of built, like we talked about, standing on the shoulders of giants. Robert O. Becker did a lot of really great work, and I've been trying to get through that Body Electric book. But what clued me in that he's not completely off base is are you familiar with Andrew Huberman at all?
That, yes,
The
but
Huberman Lab.
barely. Yeah,
He's
yeah.
he's a
Twitter,
PhD. He's on Twitter. He's got a YouTube channel. He's the PhD at Stanford. He's I think ophthalmologist by trade. But he's like the health guru, right? Like that he's got the biggest podcast around health and nutrition science. And he and Rick Rubin and Jack sat down for a 5-hour podcast. It was broken up into multiple segments. And I have never seen Andrew Huberman absolutely, I want to say humiliated. That's not the right word, but just beaten down. And he was like taking notes the whole thing. And he is just I'm here to learn. I'd never seen that side of Huberman before. He's always, positions himself as the authority. Like I'm on top of the cutting edge science. I know, and Jack just schooled him, frankly. And so I'm approaching Jack's work with a lot of trepidation and caution. But also I do know that when somebody, like we talked about earlier, when somebody has, ideas that are very far outside the mainstream, they could be completely right, or they could be, somewhat unfounded and unhinged. And so I'm still trying to work my way through his material and figure out, does it have, I know it definitely has merit in some aspects, for sure. We know this for sure. But broad applicability, do the claims that he make about our ability to be a multiplanetary species as currently constituted, and some of these other things, I really love somebody's expertise who's way smarter than me, like you. So I will certainly circle back on that one.
One thing you just mentioned about Huberman was if he was taking notes and said he was there to learn, that's a very powerful, positive note on Huberman, because
for sure.
that's how we go ahead. It is if you're confronted with something new that might confront your own personal views, and you've got and the person has data to back it up, rather than digging your heels in the ground and trying to defend yourself or win. Good for him. That's great.
Yeah, no, it was a fantastic conversation, and much like talking to you, I have to like go back and scrub and try to like Google all the terms and try to figure out what they're talking about, because it's very difficult to keep up with if you're not a subject matter expert in that space. And so doing my best just to hold on by my fingernails and glean what I can. But super interested in it, and I think that you probably would be as well. I think this is a super interesting topic, particularly when you overlay the other dimension, which is consciousness, which I know that you care a lot about. You posit the existence of a soul, and you're interested in the concept of consciousness. I had Sterling Cooley on my show a couple of times, and he works with Stuart Hameroff and Roger Penrose with microtubules, right? And they have a theory around consciousness originating in microtubules, due to the van der Waal effects, sort of forcing the wave function to collapse essentially at specified intervals, and creating little flickers of consciousness, right? And I've learned that microtubules appear to communicate or be a medium whereby internally we transmit ultra weak light as signaling mechanisms, right? And that's something that Dr. Jack also claims as well. And apparently there's experimental verification due to photon amplifiers or something like that. I can't remember what it is. There's a bunch of things that are tied to it, but I'm seeing like your work, and then the microtubule work and Jack's work all kind of connected from a physics perspective. So I would love to throw that your way sometime and get your opinion.
Yeah, I don't know Jack's work, but I do know I brushed up on the microtubules,
Hmm.
and to me, it's another one of these efforts where it appears that we don't know what the cause is and what the effect is. And in my view, and you could probably tell me more about this after our last conversation, I became aware that you've had some DMT experience,
Very
but
recent, yes.
yes, and I myself, when I was young, I had an out of body experience after an accident, and those experiences to me were one piece of evidence that there's something more to us than the physical body that we inhabit. The microtubule theory is that by studying the brain, and the same thing with the spirit molecule, by studying its chemical reactions and then what people see and that sort of thing, it's trying to understand the hallucinations or delusions that people have, that they are more than just a physical body. But my take, certainly when I had the experience of the out of body experience, I could see myself from above running. I just have a hard time believing that that was just something that was divorced from an entity besides the body that I have. And I don't know if when you had your experiences, if you had the same rather certain sense that you were seeing something real.
Yes, and that's the interesting thing about DMT, is that everybody who has taken it that I've talked to or seen reports online about has the same response. And you can even look at Dr. Rick Strassman's work, who originally studied DMT. Uh, all the subjects said this was the most real thing they've ever experienced. There's a hyper real aspect where you almost feel like, wait a minute, this waking consciousness that we inhabit day to day, that's like the shadow world, and this other place you go is actually the most real place.
Yeah, yes, that's the stance that I take, and it ties back into something else I mentioned on your show the last time I was on, about an experiment I did with my sons to turn pennies over.
Hmm.
They were all young, and I asked them to turn them over, all heads, and one did all tails, and it was 100 out of 100. And if you're a physicist and you were to take an experimental result and you get 100 out of 100 of something, you definitely say something is there. Now, people can kind of scoff at that because you say, well, of course they can turn over 100 coins. But then I expanded it, and I mentioned this on your show last time too, because I recently watched it to see what we covered. When you're typing out a single tweet, right, 280 characters, you've got about 100 choices on each character in front of you. And if you calculate the odds of getting the 280 characters all right that you have there, it's a very, very large number. But you can even expand that further because you didn't have to type the letter A in the middle of your sentence. You could have gotten up and taken a walk. You could have taken a nap. You could go get something to eat or drink or do whatever you want to do. So at every instant in time, we as a human being have in front of us an enormous number of choices that we could make. And when you end up with the works of Shakespeare or War and Peace, you end up with something that the odds of it being produced, I believe, are well beyond proven to be something that cannot be randomly generated. And so if you have that knowledge, to me at least, it proves to me beyond any scientific doubt that choice does exist. Something within us leads to the ability to choose. And that's okay. But what is it? What is it that enables us to choose? So my belief was when I had that experience that we do have something within us that is more than just the chemicals and atoms and things bouncing around. And certainly it's not, in my mind, it's not determinate. Now, relativity is a determinate theory, but quantum mechanics is not. And that's kind of where the overlap comes with this microtubule stuff, because they're also putting quantum mechanics into the mix. But for me, it's the soul that makes the decision for the quantum system to go one way or another. That is the essence of what allows choice. I don't think we're going to find that the AI systems are going to actually be able to think at the end of the day. They try to mimic the action of neurons in the brain, and that's why they're called neural networks. But they are likely to lack the soul. Now, I don't know, of course, because you may know better than me because you're on the DMT side of things. I don't know if some being from out there would invade the neurons of the AI system. Then it could happen. But if it remains soulless, I think all they are right now is a giant fitting algorithm that uses somewhat of I guess the word might be sloppy, but it's kind of a hyperbolic tangent instead of a step function. So it's rounded off, and so it ends up being spookily good at imitating things, but I don't know that it's going to produce anything. Whereas we humans, we do, and I don't know that the AI is going to be able to make a choice, but we can. And so it's that interplay between those two lines of thought that contribute strongly to my belief that a soul does exist. And in my case, again, the soul is that which has the ability to take a quantum state and have it collapse in a preferred direction, one way or the other. And from there, it's similar to what the tubular theory.
Microtubule theory.
There you go. Yeah, what that one states, because once you've got that initial action, then everything cascades down to moving your fingers. Right?
Right. And I guess the question would be is like, what is the soul and where would it even reside? Right. That's interesting, especially in the microtubule world, because one of the super interesting things that came out of the microtubule research, I don't know if you know, but Stuart Hameroff is a anesthesiologist by trade. And so one of the interesting things is you can take something like an inert gas like xenon, and that actually interferes with the collapse of the wave function of microtubules and causes the consciousness to blink out, even though it's an inert gas. It's not interacting biologically whatsoever, and that causes a complete loss of consciousness. So
Yes.
where like if it's not in the microtubules, okay, cool. Where is it? Like where would the soul reside, and how would you know like where? Like I don't understand like I get what you're saying, and I know that your last podcast, the host asked you to look into Friston free energy principle. You might want to take a look at that, because that is something I had a guest on, Stuart Sims, a couple weeks ago, and he was a proponent of that, and I looked into that, and that's a very interesting theory that goes into choice, right? This exact question you're talking about: what is actually making the decision? Is, and how granular does that get, and is it, ubiquitous throughout the entire universe at small and large scales? And that's what the Friston's free energy principle states, essentially, is that everything is making a choice. Not a
Yeah,
human with a soul, but like literally everything. This is like fundamental to everything in nature.
yeah. That I did look into his some. I don't know. I follow Philip Goff on X too, and that sounds like it touches on this whole idea of panpsychism.
A
And
little bit, but it's different.
okay, because that's where everything has, in any event, I did check it out, but I didn't think it aligned with what my thoughts are. My thoughts are that the soul exists of, so the soul does have this ability to interact with material that we're familiar with in physics by collapsing the wave function. But that's its only interface with that substance. Similar to how we discussed earlier today about an Aetherion taking up a larger size and being able to exist within the solid lattice, you could also have another substance, a soul, that also overlaps with the same space of your body and mind. And it then would act through these preferred collapses to enable all of your choices, but that's the essence of what you are. And so it diverges some from Descartes' dualism, where his idea was more that there was a separation between body and thought, and so the thought was immaterial. In this case, you would have another realm of material entities that only interact through this quantum collapse capability. It has certain, to me, somewhat positive relationships with some of the things that we see. For instance, an Alzheimer's patient, if this material body then does function in this way, as portions of your brain would become disabled, that does not mean that the soul itself would forget the things that your body is forgetting. It means that the antenna to your soul has deteriorated. Similarly, with what you mentioned with putting in, I forgot what you said interfered with it. It was some sort of gas, was it?
Xenon gas. Yeah, it's
Yeah,
an inert gas.
yeah. That could perhaps, again, interfere with the antenna, basically between what your soul is and your physical body. And it would explain that too, in my view. And most of the efforts made by the scientific community go back to looking for consciousness as more of a material effect in the materials that we are presently aware of. And so there's been an abandonment of Descartes' original dualism. And the reason I settled on the materialist view of the soul was I do also like the argument that if anything does exist, it must have something that makes it up. And it wouldn't necessarily have to be a physical entity that we think of in terms of matter particles. It could be waves or motion of existing things. But I believe that separation of realms does answer a lot of questions. So that's kind of where I am on that whole question. And it ties back into our argument before, because we never quite got to the one about being a theist, is once you accept that we have this other entity, and you've experienced it as I have, then I still think that mankind is probably not that advanced of a life form, and I'm easily capable of accepting that there's one far greater than me. And if that being or beings was kind enough to allow us a savior to follow, and by giving us great instructions. It's kind of beyond our pay grade to know what the Father is, but certainly the fact that there could be one is something that I don't have any problem believing in once I've accepted this dualistic view of what reality is.
Got it. You said a whole lot there. So touch on one thing. So would you be open to the idea that microtubules are the receiver, or like the antenna, the recipient of consciousness, like tuning into the frequency of the soul type of thing? Like I don't understand exactly what you were positing there.
Okay, so the microtube, I could strip over that word every time now. But that piece is what, if it's in a quantum state, is what the soul could then exercise its will upon to make it go into the state that it needs to have in order to exert its will.
Got it. Okay. I'm just trying to wrap my head around what I know about this. So interesting component of this is that are you familiar with the van der Waals effect or van der Waals force?
I know, yeah, I know what it is. It's pretty weak in short range.
Yeah, that apparently is what is hypothesized to collapse the wave function at specified intervals. So there's these megahertz frequencies and gigahertz frequencies that they can pick up on now. Matter of fact, they just experimentally validated this. There's this guy, I can't, he's an Indian gentleman. I'm sorry, I can't remember how to pronounce his name. Who figured out that you can put a spectrum analyzer to somebody's temple, and you can actually see these triplet to triplet patterns that are exactly at the frequency. He's experimentally like run current through microtubules in the laboratory and found out, what frequencies are operating at, and they can detect them via spectrum analyzer. We can see this thing when a conscious patient is just in waking state, and then when they're under anesthesia, they'll do the same measurement. Gone, right? The signal is gone. Then when they come back out of anesthesia, it comes back again. So that's one of the experimental ways they've sort of validated that microtubules at least have some relationship to consciousness, right? And so I'm just trying to like take that experimental data and mental model and overlay that as far as what you're positing with respect to a soul. So the soul, I guess you would say, exists. I don't. Is it locally existing within your body? Is this a different dimension? Like how do you conceptualize like the soul?
Vast majority of the time, yes, it's occupying your body. When I had the out of body experience, it left it for a while, and then
That
it.
is. Oh man, I want to get you to talk directly to Sterling Cooley, because he has created out of body experiences just by stimulating his vagus nerve with an ultrasound device while doing Wim Hof breathing.
Okay.
And he has his own theory about these megahertz and gigahertz frequencies that are related to consciousness escaping essentially the cranium, right, and then being non-local. And he's also induced remote viewing events, which sounds crazy, but I also know that the CIA was legitimately looking into this for quite a while, and there might be something to this. But he's personally expressed to me on my show having an out of body experience after stimulating his vagus nerve with that ultrasound device, where he ended up in it was Central Park in New York City. Complete, same thing, like hyper real, almost like that DMT type of thing. The same description as you would have with an out of body experience or near death experience, and he was able to reliably induce that in himself. And so he is taking a different approach. Like I don't know. I'll have to ask him, but I don't know if he posits that a soul exists. But I think he's trying to at least explain a mechanism by which consciousness can escape the confined wetware of our skull.
Well, it's not, if there was distant viewing, that would seem to be, and it's verified and repeatable. That would seem to be evidence,
Mm-hmm.
and it would be evidence of something outside of your body. It would not, because I don't see how that one's going to be explained easily by the community that wants to think all of these things are delusions or hallucinations, because the delusions and the hallucin, and that was the one with me seeing myself running, was it's hard for me to see how that delusion is going to be as good as it was. I suppose you're running maybe, but certainly this one's even more so. If you've got remote viewing and you see things that are happening, where your eyes couldn't possibly see them. Yeah, that so in my way of looking at it then is that that would seem to be some evidence that there is an entity separate to our physical being. And if
I
you
mean,
want,
maybe, or we just found a new way that the human body works, essentially, right? Our cognition apparatus,
well,
you
you're
know.
right. And that, by the way, puts your finger right on it, which is when you're having an argument about theism versus atheism, you can
Mm.
always come up with an argument to for the other side. It's one of those, at least from everyone I've seen. And now some are bad, some aren't good arguments, but when you get into the deeper ones, you're right. You could say that the human body somehow has this antenna capability beyond us. Uh, yeah, that's another
Yeah, because
proposal.
I think you're right, and I think a lot of those discussions devolve into contests, right? It's like
Yep,
I want to win. Like I
yep.
represent the new atheist movement, and I'm here to destroy your stupid worldview with my rational approach to this, and I'm going to win some points for my tribe, right? And I don't take that approach, man. I think that's so dumb. I technically am an atheist. I'm agnostic. But I'm curious, man. Like I'm open to it. Like I've been pretty dazzled by my psychedelic experiences. My mind has been open, and I really want to know. But there's something going on. I've been convinced, and like I said, I always caveat this with, okay, I was on drugs, but I've had enough experiences that were so profound, palpable, like visceral, and come through with that sense of ineffability, hyper realistic nature, and this motif of it being divine, if that makes sense. I'm not like, it's weird. I'm an atheist using that term, but it feels special. It feels important. It feels, if you look at the studies, like the Johns Hopkins University, for example, did a ton of psilocybin research, and everyone that did it, I think that they said it was in the top 2 or 3 most, a profound experience of their life, on par with, the birth of their first child or getting married. Like it's that level of importance. So it's like there's something there, and I just want to interrogate what it is because, like I said, I'm a curious person.
Yes, sir. Yeah, there's some deep mysteries.
Have you ever had any psychedelic experiences?
I have not.
Would you
The
ever
only
consider it?
I have not. No.
No, I said, would you ever consider it?
Oh, I, not at the moment. That's for certain. I'm for the most part. I mean, we've now gone into speculation, and it's and I suppose that would be data points. I kind of like the fact that I can get the data for the most part from other people, and I've had enough of them now. I see it. Aaron Rodgers being one of the most famous now.
Yeah, yeah.
That you can get a lot of data that way. I don't know that I myself have to dive in, but because I did have
And,
the one, and that was pretty change. It changes your outlook. Once yeah. Go ahead.
and that's why I'm raising this, right? It's like, first of all, I'm not trying to convince you to do it. I guess I'm curious. Chris Williamson had Richard Dawkins at a live event, and he said, "Hey, would you ever consider doing psychedelics?" And Dawkins like, "Oh, I don't know." And then he was like, "Do you ever wonder why people want you
Yeah.
to take psychedelics?" Right? Like
Yeah.
he didn't really grok that, but I have a similar feeling towards you, like somebody who is super interested in these things and has tons of theories about how this stuff works. Having that experience, because it's not the same as a near death experience. Like I think it's in the same category. I don't think it's the same thing. And so I would just love to see, like, how, if you had that experience, what your take, like if your mental model would have shifted from that experience. And the other component that's interesting and noteworthy is, before Nixon outlawed psychedelics, there was a lot of research in the scientific community, and they would bring in people, scientists such as yourself, who are struggling with really difficult problems, and oftentimes they would have a breakthrough. Like they would have the
Oh,
psychedelic experience, and it
mhm.
would, because it connects various parts of your brain that don't normally communicate with each other, and it sort of it shakes the etch a sketch clean to some degree, and you can get different insights that just come out of nowhere, and that's very common to sort of have that breakthrough. And so, from a scientific perspective, for somebody who's struggling on the frontier of something new, I would just be super interested to see if you had any new insights or updates to your theory based off of that. That's just me being curious.
Well, that's a decent argument. I guess the reason though they want Dawkins to do it is because he's
Mr.
manifestly
Atheist.
yes, yes. And when you go there, you may believe in God. But since I already do, I'm less likely to be the one that you want to do that. But your point
Oh, I
about
disagree. I disagree,
oh,
right? And
oh,
here's why, right? Because
okay.
like I think I told you, like I don't want to call myself a reluctant atheist,
Uh,
but I'm an atheist who's curious about the subject, right? And I've told a lot of people I'm open to being convinced. Like I'm not here to tear down theism. It just doesn't make sense to me right now. And I would love to have somebody present me with an argument that finally lands for me, right? Like that's kind of the way I'm looking at it. So I'll be super interested, somebody who is on the theist side or is more, faith based, to have that experience and then come back and say, hey, this is how it's changed my view, or maybe articulate it to me in a way that's different or something I can understand, or a new insight. And so yeah, I'm mining other people for for data here.
okay, I see. Yeah, very good. Yeah, I had some arguments for theism, and I'll circle around to it again when I start the philosophy portion of my feeds on X. But that would perhaps be another argument to go, that may be supportive, or in your case, maybe not. But my belief's pretty strong. So, uh, it, I, but I'm not volunteering at the moment. Put it that way.
That's fair enough, and
Okay.
that's I should probably put a disclaimer there. I'm not advocating anybody does it by any stretch of the imagination. Nobody, take that as me advocating for this, and I'm
All right.
just being super curious. So, anyway,
Great.
we're a little bit over time, man. I've kept you longer than I should have, but man, this is a fascinating conversation. I could talk to you all day. It was super enjoyable for me, and definitely have to have you back, man. So, why don't you let everyone know where to find you if they're not aware?
Okay. Yeah. It's larsonism.com is my website. That's where I've got all of my webinars and papers. They're all scientific. I don't think I dabble into the last topic at all there, but for the hard science stuff, that's where that's at. And then I'm on Twitter or X at Larson Delbert. So I like to get as many people to follow as possible, trying to get the word out, because I think I think the ether model is very sound, and I think we should return there. And also the fusion approach, I have a lot of hope that it could help mankind. So yeah, please chime in. That'd be great.
Awesome. Thanks for stopping by, man, and we will chat later.
Thank you.
Yep. Bye.
Bye.